Now, today, we plan to cover the chapter buckling, okay? But it don't take long, just 5 minutes to finish that chapters, believe it or not. So I would like to spend more time on what you do and why we are learning these all the subjects covered in this course. Well, we already know the main goal of this course, but I like to emphasize again the importance of our study in real design, relate to a real design. Okay, I'd like to share with you some practical cases in which we need to go through all the design procedure which you already went through all in design of your wing. Okay, as a first step, I like to show one of your group tasks. Group O. Who is a group O? Raise your hand. Okay. So group O. You want to show any other group who like to show your result? P. Okay. I will just briefly go through a group O. 사운드가 잠깐만. 사운드가 오디오. 사운드를 어떻게 하냐. 이 사운드가 이리 가니까 이게 안 나오네. 요거를 사운드를 바꾸는 방법이 어떻게 있나? 잠깐만요. Let's see. There must be way to change. Settings. 사운드 바꾸는 거 어떻게 해요? 아는 사람, 사운드. 그러니까 지금 소리 나는 거를 HDMI로 안 나가고 내 컴퓨터로 나가게 하고 싶어요. 간단한 게 있었는데. Okay, I will pause.
네, 이제 모델을 그대로 사용하였기 때문에 여기 나오는 조건은 이제 주어진 조건들입니다. 먼저 그 날개의 랭스는 27m, 약 27m 정도가 되고요. 그리고 그 날개 면적은 그 보잉사에서 제공한 이제 재원에서는 325제곱미터로 이제 나옵니다. 그래서 그거를 통해서 저희가 계산한 이 날개 폭은 5.98m가 됩니다. 그리고 저희가 이 날개 가해지는 이제 최대 부하를 저희가 그 MTOW, 그러니까 최대 이륙 중량을 기준으로 저희가 산정을 하였는데요. 이 값은 왜 저희가 이 값을 선택한 이유는 이 값이 이제 항공기가 그 이륙을 하고 이제 하늘 날 때
So
가해지는
as you can see that
그 과정 중에
when you have a certain project
때문에 저희가 이 값을 기준으로 했습니다.
and you design yourself, the most difficult part and important part is to look for the information. You used to start to solve the problem when with given practice, given information. 항상 여러분들이 문제를 풀 때는 모든 정보가 다 주어져 있었죠. 이제는
엑셀에서 입력한 값은
패러다임이 바뀌어야 돼요. 여러분들이 생각하는 게 정보를 찾아내야 돼요. Right? You need to look for the information.
여기가 이제 엑셀에
근데 어떤 인포메이션을 찾아야 되느냐? What kind of information do you need to look for? Geometry, material properties, and load. 네? 항상 이거를 찾아서 디자인을 시작을 해야 된다는 게 중요한 포인트예요. 어떤 그룹은 길이가 얼마예요? 그걸 왜 나한테 물어봐? 하중이 얼마예요?
cm 세제곱입니다.
무슨 말 하는지 알죠?
여기서 이제 저희가 사용한 날개 답변은
그러니까 이런 거 NACA의 441
에어풀 영상을
NACA 412 Y.
저희가 프로그램에
Well, that's your role. Why do we need to choose this one?
2에서 그 4412를 입력해서 이게 NACA 4412에 해당하는 에어풀 값을 이제 입력하였고 또 옵션
모양이
5에서
예쁘네.
보면은 여기서 숫자 11.868은 이 날개 가로 길이를 나타냅니다. 이 날개 이 가로 길이는
Another point is that well, this class is the solid mechanics.
논문에서 그
What the hell is the fluid mechanics? 왜 fluid mechanics을 갑자기 해서 공부해야 되지? 라고 생각하면 안 돼요.
이제 여기서 실제 날개
Solid mechanics and all multidisciplinary, you need to understand the fluid mechanics, sometimes dynamics, and all together. 그래서 여러분들이 생각의 폭을 좀 넓게 해서 엔지니어가 돼야 돼요.
되는 그 비율을 저희가 적용을 하였습니다. 그리고 다음은 저희가 가한 이제 하중인데요. 이거는 아까 저희가 그 최대 이륙 하중을 기준으로 계산을 하였습니다. 그래서 최대 이륙 하중 227, 약 227톤 정도 되는 그 하중에서 그 날개 한쪽에 걸리기 때문에 그 값을 반으로 나누고 그리고 전부 20개 노드에 가해지기 때문에 이것을 20으로 나눈 값인 0.0558 메가뉴턴이 각각의 노드에 가해지게 되어서 다음과 같이 설정을 하였습니다.
Okay. Here I want to say one thing. 여기 보면 if you look at this, all the load are same. 여기 보여요? 하중이 다 똑같죠? Well, that is a certainly one way. That is a certainly one way. But if you look at 다 값이 같아. F3가 뭐예요? Z축이에요? 압력이 다 같다고 쳐도 여러분들이 이렇게 윙이 이렇게 돼 있잖아요. Let's assume all pressure is a constant, uniform, but this will model as the line. 그래서 이만큼의 가해지는 force가 그러니까 여기에 가해지는 force는 여기 엘리멘트 이렇게 했을 때 요거의 반 해서 요만큼이 여기로 들어가는 거예요. 왜냐면 this one model as the line, right? So all the load here. 그래서 여기 here the force you apply is the I'm going to redraw. Let's say this is the element line, okay? The same as here, here, here. Now the force applied here is that 요거의 반 정도, 요만큼에 해당하는 force가 여기에 들어가요. And 여기는 here, say we have a node here, 요만큼. 그래서 about the same, I mean middle and here it goes to here. As at the end here, 항상 load가 이렇게 작게 들어가요. But that is not the major point. Major point is the load. When you apply the load here, you have to consider total area times pressure. Okay? I'm not saying it's wrong, but this is the one you better consider.
이제 저희가 그 두께에 따른 디플렉션 그 미터 단위로 나오는 이제 디플렉션을 만들어서
여기 무슨 조라 그랬지? 5조? 5? 나한테 카톡으로 그 포스트 프로세스 txt 그 인풋 파일 2개 만들어주는 거 있죠?
엑셀로 직접 추세선을 구해서 그
그림 그리려면은
선형 보관
텍스트 파일 2개 만들어주잖아.
그 구한 값은 T값이
몰라?
0.012927이고 그때 그 디플렉션 값은 0.9.
아니 모르면 모른다.
그러니까 1에 거의
몰라? 요 2개 만들어지잖아. 요 2개.
그래서 이걸
만들어지지.
통해서
지금 나한테 카톡으로
다음과 같이 나타났습니다. 역시 T 딱
아무거나 아무 캐스나 좋으니까 카톡으로 나한테 넣으라고.
0.12729로 이제 입력했을 때 다음 보시는 것과 같이 0.999m로 이렇게 디플렉션이 나오는 것을 볼 수 있습니다. 그 다음은 이제 전체 이 날개의 하중을 구한 건데요. 값은 0.
So this one is the one in model.
같이 나타났습니다. 역시 T 딱 값을 0.012729로
좀 보내라니까.
이제 입력했을 때 다음 보시는 것과 같이 0.999m로 이렇게 디플렉션이 나오는 것을 볼 수 있습니다. 그 다음은 이제 전체 이 날개의 하중을 구한 건데요. 각 노드에 대한 이제 하중 값이 있습니다.
오케이.
이상으로 제 발표를 마치겠습니다.
보냈어? 인터넷. So
today we'll be starting.
As I mentioned, I'd like to show you some real practical cases. Okay, all cases are from current research project which our group is doing right now with all companies, including Brazil company, French company, German, and Korean. The reason, again, I'd like to show you these cases is that, by the way, this is my personal computers. And we have many different folders, as you can see. And currently, we have 36 projects ongoing. 지금 36개 프로젝트를 우리 실험실에서 지금 하고 있어요. 누가? 대학원생하고 나하고. Anyhow, I'd like to pick some cases and to show you. One of them is the project with the Embraer. Embraer is that thank you. Okay. Embraer is the third largest airplane company. Boeing, Airbus, and Embraer or Bombardier. So third largest. So we have a very close relation. 우리 학생이 가고 그 학생이 여기 보내고 직원들이 보내서 we do a project together. So they are developing a lot of airplane. And Brazil is very well known for, they have a lot of high tech in airplane. But anyhow, this is a current project with the Embraer. And this is the real structures, cross sections of a wing. And as you can see that, this is a part of a wing, and you can see how large it is. And very interestingly, we have this kind of a box. We call box beam. This box beam is a part of this wing in the nose and edges. And so this part is a major structures which will support all the lifting force. This skin is just a skin which will control the airflow. 그래서 이 윙의 대다수의 하중은 이 박스빔으로 하중을 받는다는 거 중요한 겁니다. 아셨죠? So this is the main part of the design, skin. 그러니까 이쪽 스킨이 보면은 바로 요놈이에요. 요거를 자세히 보면 이렇게 돼 있고. 그러니까 it's not just a skin, it has a lot of stringers and increase a bending stiffness. So there are several issues we need to consider, but again, wing is this is a design procedures, a little more complicated than you do, right? But main point is the load cases. We have so many different load cases, and of course the geometry, and of course the material properties. See, exactly the same procedure as you do. You choose the geometry, you choose the material properties, and consider all different loading cases. Well, you certainly consider only one cases, but in practically, you should consider many different loads. You know, the landing, or takeoff, or gust, a lot of very strong. And then, what is this? 3D beam is the one you are using. So I do use it. We use this one to real design of an airplane. And then you get the deflections, and you get the stress, and then there is a condition, safety factors. And so these procedures are pretty much, so what you do is pretty much the same as a practical design, okay? So that is one thing I want to emphasize. So what you do is just not just for the, your homework. It is really for real design. And of course, there is a little more detail. Say, oh, there is a impact, and then what is going on this skin? That is the extra point. But this is one thing I want to emphasize to you. Okay. 이건가? 어디였지? 너? 이건가? Okay. Sorry. 왔나? Okay. So this is the airplane. 이거 맞아? Okay, this is the airplane, Group O design. Interesting. And you can see that airfoil, right? Airfoil. And one thing I want to emphasize is that the airfoil, this is a NACA 4412, right? But NACA 4412 doesn't have to be constant. 그러니까 여기서부터 여기까지는 낙하 뭐를 쓰고 여기서부터 여기까지는 다른 걸 쓰는 예가 대부분이에요. 네? For your informations. So this 낙하 airfoil can change from station to stations to increase more efficiency. Another point I want to emphasize, as I mentioned, is that this is N1. What is N1? N1 is the bending stress. Bending stress multiply thickness. That's why the top skin, what's happened? Top skin. Compressions, right? What happened to bottom skin? Tension, right? So look at the value, and blue is a minus 1.66, and the bottom is a lot of what? Tensions, and tension and compressions. Is that okay? Yes, you can. You don't know exactly the numbers, but you understand why bottom is the tension and top is the compressions, and why here is the maximum, why there is a maximum. Can anybody tell me why maximum here, maximum there? See, the neutral axis is somewhere. When you consider bending, you always consider the neutral axis. Neutral axis and how far from the neutral axis. It gives us the strain, it gives us the stress. Okay. So here, say this is the neutral axis. Okay. Here is the neutral axis, which we don't know exactly, but it has to be neutral axis. Now on the bending like that, and this here, there, 여기가 가장 높죠. So the farthest point is here. That's why we have a high compressions. At the bottom, well, approximately here is the far point, and here is the most of the tension. So if you look at here, and that is subject to a compressions, and look at here, the skin is the under tensions. So from this result, well, it's not easy to predict numbers, but qualitatively you should understand what is going on. Okay, this is important observations. And another observation you have to pay attention is that, shear flow. Shear flow. What is a shear flow? What is a shear flow?
Well, shear flow, what we learn from the class is that this one subject to a huge upload, right? Upload. And then, okay, all the shear force from the pressures comes from here, right? And now imagine how much shear force in each cross section. So in this cross section, we have to have this much shear force, which will be the same as this one, right? That's the shear flow. And so all the shear flow mainly supported by this shear web. Remember this I-beam, all the shear flow is at the maximum at the middle, right? Where is the neutral axis? 중립축에서 항상 shear flow가 최대라고 배웠죠. That's why we have a so very high shear flow, okay, shear flow, and then goes like that and goes like that, and it goes very small and something like that, okay. So understanding shear flow is important, and understanding bending stress is also important. So you consider 2 points in design. First one is how much you deflect, right? If the wing does not fail, but if you deflect like that, we don't like it, right? So we have to have a certain limit. And even though it does not deflect much, but there will be huge stress, it may break it, right? So we have to consider safety factor. So stress, we have consider a safety factor, and deflection, we have to consider a maximum allowable deflections. Those are 2 factors. But in real situations, as I mentioned, using these real flow charts, see what I did. I draw all by handwritings and consider all real situation. This is a box beam. You can consider, you can have a front and here, okay. This is the airfoil. So, where is that? Okay. So when you design, as I said, you consider deflection, you consider stresses, or sometimes a strain. And another thing is you need to consider is the buckling, which in our case, we need to study a little bit about the buckling. And sometimes we have to consider, well, flutter frequency. What is that? Frequency. Well, this is another interesting features. And 이쪽으로 와.
그 세 명 다 앞으로 오세요. 이거 더 잘 보여. So when you design, there are two factors you consider, deflection and failure stresses. But another one is the buckling, which we will study. And another important is the frequencies. What is this frequency? Every structure has its own frequencies. Imagine that we have a spring and mass. Okay, spring and mass. And you stretch and let it go. What happens? It vibrates, right? It vibrates. But how fast? We don't know. The frequency is the speed of a vibration is determined by how heavy. What's the spring constant? So this K and mass will determine is how fast it vibrates. Exactly same for the airplane. If you make very thick, very heavy, thick stiffness, it always has its own vibration mode. So this one has nothing to do with the external load. 외부에서 하중을 가한 것이 아니라 이게 it has its own frequency. So if spring and mass 내가 만약에 여기가 지가 떠는 속도랑 같이 어플라이 하면 어떻게 돼요? 공진이 일어나요. 왜냐하면 이거 없이도 without any external force, 이 system has its own preferred frequencies. 아무것도 없어도 잘 떨고 있는데 외부에서 그거랑 똑같은 걸 떨어봐요. 얘는 그냥 얼싸 좋다 하고 그냥 춤을 추는 게 바로 공진이에요. So you have to avoid natural frequencies. avoid this external frequency하고 자기의 frequency하고 맞게 하면 큰일 나요. So in the airplane, let's say you have an engine, you have a frequencies. If this wing has the frequency same as that, big trouble. The airplane will go crazy. So which you don't like it. So when you design, you have to consider all these stresses and shear flow, bending stress, and how much it deflects, right? Deflection, how much it deflects. So you have to consider that. But at the same time, as I mentioned, you have to consider a mode and it has its own frequencies. It like to vibrate. Say 1 time per each second. 1초에 한 번씩 떨고 싶은데 외부에서 somehow you apply, 그러니까 바람이 불든 뭐가 오든 1초에 똑같이 이거를 땅땅땅 때렸다가는 어떻게 돼요? 큰일 나요. Okay? We'll be in big trouble. But this is only one mode. But there is another one, which is like this. 더 빠르게 떨어요. And we have so many high different modes. And sometimes this is a first mode, like to vibrate, and sometimes you have a different vibration, like this. Okay? And this frequency is different. 이거는 1초에 예를 들어서 2번 떨어요. 좀 빨리 떨어요. 근데 더 빨리 떠는 거. 그러니까 all these structures has their own natural frequencies, many natural frequencies, many. And sometimes there's a twisting. So it's like this, and like that, and like that. It's like a break dance. So you have to consider, okay, there is a certain external frequencies, and now when you design, you have to avoid. How to avoid these natural frequencies? Well, you have to change the skin thickness, and you have to consider all the weight and stiffness. Okay, so this is another design constraint. So as I mentioned 5: deflection, failure index, buckling, and these vibrations. Any missing? Okay, 4. Okay. Of course, there is another one, but this is 4. Which one is that? Well, that is exactly you need to understand when you design a certain structures. Okay. Prepare for the final exam. So this is the one example of the wind turbine blade. Again, you always consider geometry and material property, and most important part is the load you apply. It was not easy to find the right load. Well, that's the very difficult process. Now, different structures. For example, let's say this is another project we do right now with Arkema. Arkema is the French company, and which developed materials. Well, this one, after this class, I will fly to Germany and present about this wind turbine blade. And this is December 12. And this is about all the materials, plastic. So they developed very different plastics which can be applied to wind turbine blade, or a bike, or airplane, or ski, all sports goods. And this is the composite. Composite is a fiber and resin, plastic. So Arkema is a very famous company, and developing plastics, and we are working together. And our role is to design a wind turbine blade. We design how long? 100 meter. One blade, 100 meter. How long was your blade? I mean, your wing? Boeing 787. 30 meters, right? 30 meters. But this one, you can see that how all part we consider thickness. This part, that part, we consider all the thickness, and most important, typical part is wind. How much wind we have to consider. So this wind also obtained from simulations. We have a design tool which would generate wind. So all random fatigue load, and then as you can see that we consider all failure index and deflections and
little more, we do consider real, when it fly, I mean, wind comes in, wind. This is exactly the same. Airfoil. Wind comes in as a lifting force, right? Lifting force, it lifts and then it rotates. That's how it generates all electricity. Because here and at the center, we have a generators. All the spins, you have to generate. So, trying to emphasize the major steps you've been through in design of Boeing 787 is exactly same as design of other structures. Geometry, material properties, and load you have to consider. And then try to minimize the weight. Okay, try to minimize the weight. That is the another practical design process. Speaking of a wind turbine blade, 이게 그냥 보면은 별로 크다라는 생각이 안 드는데 this is a real airplane. Just one blade is a 57이죠. 아까 설계한 게 얼마였어요? 100m. 그러니까 전체를 보면은 요거는 이 비행기는 진짜 윈 터바인 블레이드에 비하면은 세 발의 피해예요. Imagine that this is the Statue of Liberty, 자유의 여신상 알죠? 하고 어디 갔어? Well, 요게 요만한데 실제 지금 우리 설계하는 건 이만해요. 엄청납니다. So this much big, large scale. Imagine how heavy it is. 30 tons. 블레이드 하나가. 이게 계속 돌아야 돼요. 이너시아 폴스가 얼마큼 되겠어요? So who design? You. 메카니컬 엔지니어가 다른 엔지니어들은 못해요. Only mechanical engineer can design this kind of big structures. Why? Because we do know mechanics. We do know about the mechanical properties, stress and strain. And we know the Mohr circle. 다른 전기과가 하겠어요? 뭐 전자과가 하겠어? 토목과가 하겠어? 전부 다 기계공학과들이 비행기 설계하고 only mechanical engineer can be able to design airplane and wind turbine blade. 그 다음에 또 여러분 그 요트 경기 봤어요? 요트 경기에 이 디자인들이 전부 다 누가 하냐? 전부 다 메카니컬 엔지니어들이 하고 아메리카스 컵스 이거가 월드컵처럼 아주 유명한 이게 경기의 룰을 딱 정해놓고 딱 해서 이제 요청하는 건데 얘네들이 디자인을 해서 뭐를 지금 얻겠냐고 하는 거죠.
differentiate ourselves, and hence we put all our research is the dagger balls and the wetted surface and drag that they entail.
그러니까 일본 그러니까 전 세계에 날고기는 이 그 요트가 와서 이제 전 세계 경기를 하는 거예요.
To understand a sailboat at a really fundamental level.
So what they do is pretty much the same as we do.
That are moving at different speeds. So we have wind blowing across the water, and we have effectively two aircraft wings. One operates in the air, which is the sail we see.
이 오른쪽 날개 왼쪽 이게 보여요? 이게 옛날엔 요트가 물속에서 물속에서 떠서 갔죠. 이제는 날러서 가요. 딱 요것만 물속에 딱 하고 이렇게 전체가 들려서 날러서 가요. 그러니까 이게 에어폴이 해가지고 쭉 가고 이게 아주 재밌어요.
That is simply moving the lightest conditions. We need to be able to race between 6 knots of wind and 25 knots of wind. 6 knots of
가는 거를 좀
we can't fly the hull, so we're 2 hulls in, we're very slow. It's pretty painful. Things happen very quickly from there on up. You know, about half a knot.
그러니까 이게 하중이 so much wind force is so high, and this is there is a mast. 마스트 굴지를 어떻게 설계를 할 것이냐. 이거 지금 붕 뜨는 거 봤어요? 지금 붕 떠서 날아가죠. 요트인데 거의 플라잉. 이거 보세요. 거의 날아가요.
Is apply what we call rudder differential, but that is have a difference in lift from the leeward side of the boat to the windward side of the boat on the rudder.
이게 요트 has a special features. 요트는 이제 바람이 불면 바람에 따라 이제 이 flies and sail. 근데 바람이 이리 오는데 이리 갈 수도 있어. 바람이 남쳐오는데 이리 가요. 약간 뭐 여러 가지 디자인에 따라서 물론 이렇게 하려면 이렇게 가고 이렇게 갑니다. So anyhow, it's very interesting in terms of design, especially this yacht. 이게 바로 뭐예요? It's a carbon composite. Almost 99% of all the structures made of carbon fibers is called composites. And fibers and resin, no longer metal, steel, no longer aluminum. They are old materials, now is a new materials. So anyhow, it's really fun to watch all the games, wind turbine blade or a yacht. 하여간 okay, well, so airplane, wind turbine blade, and yacht is the one structures, the one you can design. And another one, let's say, let's pick this. This is another French company called Technip. Technip is has the longest history in producing a pipe. A deep sea, 바닷속에 2,000 meter or 3,000 meter deep. What do they have here? Seabed is called seabed. 여기 뭐가 있을 것 같아요? Oil and gas, natural gas. Really big natural gas and oil. 그러면 그걸 어떻게 해? 그걸 시켜야 돼, 빨아 올려야 되죠? Yes. So this pipe is called riser. So this is a structures inside and outside, but this one has the 3,000 meter deep. 3,000m 물속이 얼마나 압력이 높겠어요? A lot. 그래서 웬만한 파이프 가지고는 안 돼요. So you have to design considering all the pressure, all the material properties, and so on. So conventional one is the all metal. But 이게 3,000m면은 압력도 높지만은 파이프 있다마는 게 메탈이 3,000m 길이에서 좌중으로 내려 눌러봐요. 당겨진다고 해봐요. Imagine how much tension load you need to support here to support all this 3,000 meter long steel pipe. Huge. Mainly because it's too heavy. So now we like to use the very light material, again, carbon composites. So we have to consider all kinds of structures and geometry and material properties and all kinds of buckling. Okay, we'll cover the buckling today and all the design procedures. Okay. See, load cases, water deep and 3,000s, and besides the mechanical load, there's an inner. 바닷속이 얼마나 차가워요. 4도씨예요. So only 4 degrees Celsius and very cold. We have to consider that. The pipe can expand and shrink. We learn about the stress strain and thermal strain, right? So we have to consider all this, and we have to consider all the external load. As an internal, external force, and bending and torsion, and tension, 우리가 다 배운 거 아니에요? Tension, bar, torsion, shaft, and bending is a beam, right? So all kinds of a load. So I like to emphasize that what you learn, what you studying is not just for your, only for this class. What you learn is really for practical design of real structures. Wing and pipe and yacht, you name it, everything. Okay, so well, you can forget all the equation. Sigma equal moment divided by I. I'm sure you will forget, but don't forget what you can do. Okay, from the knowledge, using the knowledge you learn in this class. Okay, another example, let's see. Shomarat and Beacon Power, and okay. Babula. Okay, Babula is a company which produce tennis racket. Well, this project was a little bit 2 years ago, but others is all current project, but this one was the 2 years ago. See, when you design the structures like a tennis racket, we have to have a certain shape, and when we have a certain shape, the stiffness of this rim is very critical, and this area is also has to be very stiff as well. So how do we manufacture this? What procedure we are doing? Well, we have a certain procedure for producing this a rim, and then we have this yoke or a strip and a rim. We consider all the stiffness and deflections, the deflection like that. And this is the exactly same procedure or same tools you are using in design of wing. Okay, so we do some tests, apply force, and how much it deflects, and that is another design requirement. Okay, so that is the also one interesting practical design of the tools you are using. Okay, tech. What else do we have? Okay, well, composite bike is a very, we already know that. This is a composite bike frame. Used to be made of aluminum, but aluminum is still too heavy. Now is the all composite, very light. You can just lift like that, one fingers. So this one we also design. And so the point is that how thick. Mando also try to develop. 여러분 만도 아시죠? 회사. 네? 만도도 지금 다양한 자전거를 전기 자동차 is electric bike from Mando, and they are trying to develop using very light materials. Okay, so that is the another example. Now another one, you just saw the embraer. How about the electronic applications, such as LG? Well, this is another current project. 지금 이거 하고 있는 프로젝트라 많이는 저기 하지 못하지만은 하여간 그림이 안 나와 있나? Well, when we design the structures, not just airplane or transportation or sports goods, there are another structure which is supports heavy OLED. You know the OLED screen. Monitor OLED 알죠? Very famous product in LG, and this is the one of the biggest LG OLED screen, and I'm sure you can see that in Incheon Airport. 인천 에어포트 가면은 천장에 매달려 있어요. 엄청나게 헤비, 몇 톤이래요. Now they need very light. 요새 선전하는 거 봤죠? 아주 얇은 거. 네? So they need a structures, a supporting this with a very light materials. So again, what we do is the considering design and all the law, all the boundary conditions, and how do we manufacture, and so on. So all the design procedure is not just for the mechanical part, but also electronics as well. Another electronics is for your cellular phone. Just one page I'd like to show you. Foldable display. Now your phone has to have a resistance and drop, right? And drop, and it should not break. You know, the LG and Samsung phone is very strong when you have a drop. Much stronger than iPhone. iPhone has very weak. When you drop, it break. Why? Because Samsung and LG, Korean design. We design. Well, so anyhow, now next generation is a foldable display. Foldable display. We have an old screen and fold and up and fold and like that. And now we have to consider all the stresses in here. How much, there are a lot of stresses and up and down, up and down. And this a foldable display is not just for the screen and all the clothes you are wearing. 옷이 이제 전부 다 OLED 스크린으로 가요. 또 뭔가 이렇게 패션 여러분 보여주는 거 좋아하잖아. 이게 막 빛을 딱 하고 데이트할 때 I love you 뭐 싹 하고 어? I'd like to marry you 뭐 이렇게 프로포즈도 하고. So use all your imaginations. But when you use this foldable or very flexible screen, imagine this is a buckle or pants, and you have to consider all mechanical properties. Okay, there is another one. 잠수함의 뒤에 propeller. Is a propeller. The key part of the submarine is the propeller, and has to be very strong and very light. And so they are using submarine 쫙 날아갈 때 at the end there is a propeller, right? And propeller rotate and all the water pressures and it deflects, and then there is a reaction force which the reaction force will push all the submarine. So imagine each blade how much force has to support. So all the the propeller blade and rotate and water pressure. In your case, wing has the all air pressure. Air pressure lift, right? But here is the all water pressure, and that cause the a force, thrust force. So that is the force we can calculate from fluid dynamics, and then all the forces will deflect the blade, and then we have to consider that. We have to consider all these kind of structures. This is the one of the parts in automobile, and this a Chinese company function and bumper, and all the bumpers. The role of the front bumper is to observe the impact forces, and it used to be made of metal. It's simply too heavy. Now we have to make it very light. And all these parts has a redesign and replaced with the very light materials. And imagine that when you have, this is the PDF, you can have a bounce back and forth and back and forth, okay? Okay, so I like to emphasize
all the how important design is. So all your procedure, design procedure is, I hope you practice, you go through and you practice, and I hope that you can learn general procedure of design. Now, another most important behavior of a structure is buckling. Okay, this is chapter 13, and this is the second to last chapters we have to finish. So we have about 5 minutes. We're gonna finish this chapter. Okay, what is a buckling? I'm not gonna cover all the theory, but I just want to emphasize what is a buckling, when does it happen? And you need to consider this buckling behavior in designing of real structures. Does anybody know buckling? 한국말로 좌굴이에요. 좌굴. Buckling. So what is a buckling? Very simple. Let's take a look at these structures. What? Okay. I will continue with your design. Wing. Okay. This is the a wing. We have a top skin and bottom skin. And whenever it bends, what will happen? The top, always compression, right? The bottom, tension. That's what we observed from your study, right? See again, the top is the what? Compression. Top is the minus compression. On the bending like that, it's a compression. So when we have a structures, certain structures, okay, certain structures, and I'm trying to bend. Take a look at what's happening. Always on the top where the compression is, what happens? 찌글찌글해지죠? There's a winkling. It's called buckling. Okay? This is another behavior of a buckling. So why it happens on the compression side? Listen very carefully. Again, I'm not going to cover whole class. I'm going to just explain and that's it. We have a certain load and try to apply to this structure. So this is a piece of structures. When we apply the tension, very strong and very well support tension load, right? At the bottom, it will support very well. But when it compression, it cannot support same load. Why? Does anybody know? I mean, different material properties? No. It only happens under compression. It cannot support. The reason is very simple. When we have a tension, let's say we have this much curved shape. When we apply the tension, and this point has a distance,
and then the moment will try to strengthen, try to make it straight, right? But on the compression, whenever it has, it curve, but this force will cause a more moment, and it becomes unstable. So anyhow, this behavior is very, very, very important. You have to consider in your design. Okay, buckling. Where does it happen? Compression. Okay, compression. Don't forget this. The compression. Now I'm going to apply not the compression, but the shear load. Okay, shear load. You know the shear load? Shear. Shear means that we apply this way, right? This, that, that, that. So I need your two arms. You apply here and there. This way, now you get it. 1, 2, 3. Okay, come on. What's happening? What's happening? Look at this, structures. Structures, 45 buckling, right? 45 buckling. Why? Why compression in this direction? Thank you. Huh? Why compression in this direction? When we apply the shear force, there is a compression. Why? That's exactly what we need to study. We already studied. Okay, now we applied like that. Okay, we applied like this and like that. Student apply and I apply here. Okay, now let's try to draw the Mohr circle. This is a shear, right? Shear means we don't have any tension and compression. We have a 2 point. Am I right? Right? And now we make a circle. And 45, 2 times 45, how we have a compression and tension. So in this case, is exactly same as the compressions and tensions. So because of this tension compression guy, that's what's happening. It buckled like that. Okay. So very interesting behavior observations. Shear would have compression in 45 degree, so it may buckle in 45 directions. Another one is like this, these structures, and I apply what? I apply torque. I'm applying torque. 잘 봐요. Let's see what's happening. This way is the buckling, right? This way is buckling. Why? Well, we do know when we apply the torque like that, and in the skin, we do know it has a this and that and that and that, right? Which will be the same as that one. That's why in 45 degree, we have a buckling. Okay? So this is another buckling behaviors. 얇은 볼펜 있나? 심? 볼펜 심? So this is the behavior in the skin, but major thing is that another structure is like, okay, thank you. This is the structure. I mean, it's not just, ball pen, but same behavior will happen to wind turbine blade and airplane. again, whenever we have a tension, oh, it supports very well. But whenever we have a compression, it cannot support, right? It cannot support. Why? Because of a buckling. So you have to be very careful when we design a structure under compressions. Okay? So it happens in any structures. And the tool you are using, this one, cannot predict buckling behavior. I wish I could, but right now only strengths and natural frequencies and deflection and so on. But keep that in mind, please. We have to consider buckling behavior, especially in compression behavior. Okay? Okay, that's all I want to say about these chapters. So we finish these chapters. There are some story and this and that and you know, all kinds of equations which you don't like it and I don't like it and you will forget soon. So don't worry. You can always ask Google. You can find this equation, but don't forget the concept. Buckling, when does it happen? When you design, you have to consider this buckling behavior. Okay, so that is the end of these chapters. And tomorrow, we will move to next chapters. Next chapter is the energy method. Any questions? We have a final exam. When was our final exam? 지난번에 어나운스 했죠? 오케이. 잠깐만요. Right? So we do have an exam on 13th. 시간 정했나? 7 p.m. Okay. I wish you best luck, but buckling is the one topic you have to be able to explain, okay? I'm not asking you to solve a complicated equation or a differential equation, but you have to be able to explain what it is and what you need to do in design of real structures. Okay. That's all I would like to cover today. And any questions? Yes? Yeah, we will announce. We will announce the where we're gonna have an exam. Okay, but most likely here and around this place. Okay, see you tomorrow.